Welcome to Optimization Tutorial 7, Truncated Newton and Quasi-Newton. A quick reminder of the Newton method. So given a twice differentiable function from Rn to R, we will use the following iterative algorithm to find its minimum. This iterative algorithm is the Newton method. Using the second Taylor expansion, we know that f at point x plus d is equal to f of x plus d transpose the gradient of f of x plus half d transpose the Hessian of f of x multiplied by d. And then we will define d star as arg minimum of this expression, meaning it will be the direction to take the step in that would give us the most improvement. So let's find this d star by taking the derivative of this expression, and we get this gradient. And so by equating it to 0 and finding the root, we know that the Hessian multiplied by d needs to be equal to the minus gradient. This is a set of linear equations. We can solve this for d and then find the steepest the direction for the step. But if the Hessian is not positive definite, and so the system might not have a solution, we would use modified Cholesky factorization to solve this set of equations. Because we've worked harder than usual to find the direction, in opposed to just finding the gradient in gradient descent, we would mostly use exact line search for the step size instead of just Armiot rule or a constant step size. The truncated Newton method. So, as we have seen, the Newton method is very computational heavy, and the size of the Hessian could be very big if we have many variables to optimize, because the size of the Hessian is square the amount of variables we need to optimize for. And so, we would use a truncated method to solve this problem. We would not compute the Hessian itself, but we would use a method that will allow us to compute the Hessian multiplied by a vector for a given vector very fast. If we know that the Hessian is the result of a series of multiplication, for example, the Hessian is the matrix A multiplied by a matrix B multiplied by a matrix C, then multiplying these matrices and actually computing the Hessian is very expensive. But if we manipulate the order of multiplication, we know that H multiplied by V is A multiplied by B multiplied by C multiplied by V. So if we only multiply C with V, we do a vector matrix multiplication. Then it will result with a vector. So we will multiply this vector with B, also a matrix vector multiplication. That will result again with a vector, and then again multiplying with A. So by doing that, we only multiply matrices with vectors, which is much cheaper than multiplying matrix with matrix. We would solve the set of equations that we need that the Hessian multiplied by a direction d is equal to minus the gradient using the conjugate gradient method, in which we will need to compute x transpose multiplied by the Hessian multiplied by x. So this part, we could use this method to compute very fast and then multiply by x transpose. So we would actually use the Hessian to solve the set of equations very fast, as we have seen in the conjugate gradient method in previous lectures and tutorials, but we would not compute the Hessian in any point. The quasi-Newton methods. The problem of calculating the Hessian in every iteration is it's very expensive, and we're trying to get around it. We know that the important part in the Newton method is that the Hessian, by denoting it as h, and the gradient denoting it as g, the Hessian multiplied by d is equal to minus g. So the quasi-Newton methods will try to simulate the Hessian by approximating it in every step using the information from the previous step. We will define an iteration k as bk equals to the inverse Hessian at location xk. Before dealing with the inverse of the Hessian, let's see how to approximate the Hessian at each step. So let's denote pk to be xk plus 1 minus xk, and qk to be the gradient at location xk plus 1 minus the gradient at location xk. We know that by definition, h multiplied by dx is dg. So h at iteration k plus 1 multiplied by pk is equal to qk, approximately. This equation is very important. It's called the second equation. We will define a rank 1 update, meaning hk plus 1 equals hk plus rank 1 matrix that we will denote as u multiplied by v transpose for some vectors we are not yet familiar with. And so, plugging this equation into here, we know that hk plus u multiplied by v transpose pk equals qk. Let's open up this equation. So we get hk multiplied by pk plus v transpose pk equals qk. So let's move this to this side and we get u multiplied by v transpose pk equals q minus hk pk. But we can notice one thing. V transpose pk is a scalar because this is a row vector and this is a column vector. And so let's divide by by v transpose pk both sides, and we will get that u is equal to 1 divided by v transpose pk multiplied by qk minus hk pk. And using this for any vector v, our new Hessian will hold the secant. But there is another property we can use. As we know, for any ij, hij is equal df to dxi dxj, and that is equal to df dxj dxi, and by this definition, this is equal to hji. That is meaning that the Hessian has to be a symmetric matrix. And so we will pick a vector v to make sure that the Hessian will be symmetric. So until now, we have that hk plus 1 equal to hk plus uv transpose. That is equal to hk plus 1 divided by v transpose pk qk minus hk pk v transpose. So if we will pick v equals qk minus hk pk, we will get that hk plus 1 is equal to hk plus 1 over v transpose pk v transpose. This matrix will always be symmetric. This is a scalar, and by induction, this will be symmetric as well. And that is a symmetric matrix. But we are interested with the inverse Hessian. So how do we approximate the inverse Hessian? So if we have bk equals the inverse Hessian at iteration k, then we know that bk plus 1 inverse multiplied by pk equals qk, as this approximate the Hessian, because bk approximate the inverse Hessian. And so we can infer that pk equals bk plus 1 qk. So if we notice something, we can see that this equation, if we flip the sides, looks very similar to the equation we had before. Let me remind you that the equation we had before is hk plus 1 multiplied by pk equals qk, but this time we have it flipped. So our qk and pk have flipped places, but the rest is exactly the same. And so all we need to do to define a rank 1 update for bk plus 1 to approximate the inverse Hessian is use the exact same formula, but flip between pk and qk. And so we will get the same results, but with the vectors exchange. So we define v as pk minus bk qk instead of qk minus hk pk, and bk plus 1 equals bk plus 1 over v transpose pk v transpose. So now we will define a rank 2 update. We will add more constraints to the Hessian update to get even closer approximation. So let's define another type of norm. A W-induced norm will be the Frobenius norm of a of w raised to the power of half a w raised to the power of half. We will add the constraints to the algorithm that would minimize the distance between bk and bk plus 1 in the W-induced norm. If we will use w equals the Hessian, we will get the BFGS algorithm. If we will use w equals the inverse Hessian, we will get the FP method. Note something very important. The derivation of these algorithms will not be shown in this course, and you are not required to know it. You can if you want, but we will not ask about it in the homework or the exam. So how do these algorithms look? pk and qk are defined as before. Sk is bk multiplied by qk, tau k is sk transpose multiplied by qk, mu k is pk transpose multiplied by qk, vk is 1 over mu k multiplied by pk minus 1 over tau k sk. So bk plus 1, the update would look like bk plus 1 over mu k pk p transpose minus 1 over tau k sk sk transpose plus lambda multiplied by tau k, vk, vk transpose. So this is where the algorithm differ from each other. If lambda is equal to 1, we would get the BFGS. If lambda is equal to 0, we will get the DFP. Note that you do not need to memorize these equations and their derivation. Another important algorithm is the LBFGS algorithm. As we can notice, all these methods are of the form bk plus 1 equals bk plus uv transpose for some vectors u and v. So if the matrix bk plus 1 is very big, we don't want to store it in the memory. So we have an algorithm called LBFGS, limited memory BFGS. It goes as follows. If we keep in the memory only the last updates, and we will represent in the memory the matrix bk plus 1 as just a sum of rank 1 matrices that are multiplication of some vectors u and v. ui multiplied by vi transpose plus ui plus 1 multiplied by vi plus 1 transpose, so on, until uk plus 1, vk plus 1 transpose. We will only need to store these vectors in memory. That is meaning that if the matrix bk plus 1 would be of rank k, we will only need to store 2k vectors in the memory instead of the entire matrix that could be much larger. So not only this representation requires less memory, the multiplication of this matrix with a vector that is always required to find the direction is cheaper. That is because the manipulation of the order of multiplication we can do for a vector multiplying from here would require us to do only vector multiplication, which is much cheaper than matrix vector multiplication.